My name is Hannah Bonvecchio, and this is my Lab 3 on black hole and orbits. So the purpose of Lab 1 is to determine the mass of a black hole. The purpose of Lab 2 is to find the initial velocity to perform a figure-8 orbit around both a moon and a planet without crashing. Lab 1 should be around the medium range for black holes, so from 100 to 10,000 solar masses. A solar mass is equal to 1.89 times 10 to the 30th kilograms. Lab 2, you should temporarily create a bound trajectory using a velocity that's slightly greater than the moon's velocity, but ours is a little more. The physics fundamentals that are important for this lab are knowing Newton's second law, specifically F net equals dp over dt, uniform circular motion, so knowing that velocity is constant, and F net parallel equals 0, knowing that p hat points towards the direction of velocity and n hat points towards the center of the kissing circle, knowing dp dt parallel and dp dt perpendicular, knowing centripetal acceleration, so knowing that v squared over r is a component of dp dt parallel, knowing the force between a planet and another object, so gmm over r squared times r hat. Knowing velocity and position update are also important. So let's find the mass of a black hole. In our system, we have a star and a black hole, and our surroundings are other planets, stars, or objects in the solar system. Our given information was star mass, additional information in the starter code, and the star trajectory will vary from person to person because it was randomized. So we calculated the star's change in velocity and momentum. We calculated the change in momentum over time, over change in time, calculated F net parallel, F net perpendicular, and then calculated the black hole mass. So the mass of the black hole ended up being 7.81 times 10 to the 33rd kilograms, and that is basically found by taking the average of all of the masses, and this is a distribution showing how varied that was. And then we had, and that comes around to 3,927 solar masses, which is equivalent to an intermediate black hole. So a medium black hole is a good estimate for this lab. Possible sources of error are that we estimated the actual mass of the black hole, assuming a circular orbit, assuming point masses, and maybe rounding inaccuracies. So we're going to discuss how the net force and its parallel and perpendicular components are different from rate of change of momentum and its perpendicular and parallel components. So F net is the sum of all forces on an object causes a change of motion. F net parallel is the force parallel to velocity, changes speed, and affects magnitude of momentum. The F net perpendicular is equal to the force perpendicular to velocity, changes the direction of motion, and affects the direction of momentum. Now, the rate of change of momentum is the result of F net acting on the object. Momentum's changing over time. The result of the change of momentum is parallel to velocity, and it's the change in the object's speed. Now, the rate of change of momentum perpendicular is perpendicular to velocity, and it's the change in the object's direction. So now we're going to do Lab 2, orbiting without crashing. Our system is a spaceship, moon, and a planet. The surroundings are the star the planet's orbiting, other planets, again, anything that's in the solar system. We're given the planet mass, the moon mass, and the ship mass, and other information in the starter code. And basically, we're going to find this orbit without crashing by finding the net force on the moon. So we're going to do the distance from each of the objects and do the force from each of the objects. We did it times the unit vector because we went ahead and found the magnitude. So we had to end up changing actually a portion of the code at the bottom. And then we found the net force on the spaceship, and then we updated the moon and the ship's velocity and updated the moon and the ship's position. And to basically find the velocity, we just had to plug in until we found something that worked. And what we found that worked was that it was about negative 1500, and then we found moon dot velocity plus 10,000. So a little more than just the moon's velocity, and a little bit, but that's what we found worked, and it came out to a figure 8. So possible sources of error are same as the first one, ignoring things in surroundings, assuming point mass, assuming circular orbits, and rounding inaccuracies. So would there be any dominant interactions, or would they all contribute more or less equally if it had a black hole, a star, a planet, and a moon? So basically, in this situation, the force of the black hole on the star would be dominant because it's super large mass, and then the weaker one would be the force of the star on the planet because it's opposite of the black hole on the star. And then you also have some other dominant interactions, that being the force of the planet on the moon, because it's really close. And then you had three really weak interactions. So the force of the black hole on the planet, force of the black hole on the moon, and then the force of the star on the moon.